Subramani sir already in inaugural function, and he had a session at session 1, and we welcome you for the next session, sir. Thank you.
So good evening, everyone. So this is my second session on this FTP. Some of you, or maybe most of you, have listened to my first talk, that is on the first day after the inaugural session, where I introduce you to smart grids. Though the FTP, the title of the FTP is on AI and IoT for urban and smart cities. Of course, you cannot create smart cities without having smart grids in them. So I talked about that. So in the second session, I would like to again focus on my own research area, that is power systems. I would like to talk about two applications, two important applications, though there are many applications using AI and ML, particularly in power systems. And of course, AI and ML can be applied in almost all the fields. Today's talk will be mostly on applications of AI and ML. This will also be helpful in building smart cities as well as with the help of AI and IoT. I hope there is a connection between today's talk and the title of FTP. So this is how my talk will go today. First, I will introduce you to the two applications what I have taken today. These applications are the results of my research works at IIT Patna. Of course, I do research with my PhD students and MTech, BTech students. We have been working on this particular topic for long. So I'd like to talk about the results what we have got based on those findings. The first application is state of charge and state of health estimation of electric vehicles. So that day also I talked about EVs in brief. Today I would like to focus on this particular thing. The second application what we have considered, what we have worked on is that stability, something related to stability. I will not talk in detail about those things because some of the participants may be from different backgrounds, so may not be able to understand fully, but I will touch upon in detail so that even non-electrical engineers can also understand these two applications. So this is how my talk will go. The first thing is, what is the need of using AI and ML, particularly in EV? And we are all familiar with what EVs are. Of course, it's a vehicle that uses electric motors for propulsion. And some vehicles use both electric motors and IC engines. They are called hybrid vehicles. So where we thought of using artificial intelligence or machine learning models in EVs, where some applications require some specific things. And the second part, what we worked on is stability studies, particularly power system stability. Of course, it can be applied to smart grids also. In a simple way, from a layman perspective, even though I've given a definition, clear definition of stability, in a layman's perspective, we can clearly say that power system stability means, of course, we need to get electricity all the time. If there is any problem in the grid, then customers or consumers may not be able to get electricity. That means the grid will fail. So we need to avoid the situation of failure of grid. So in order to avoid the failure situation, the failure of grid, so we need to make the system stable. That's how layman can understand this. Power system engineers can understand based on the definition. That means it should be in a state of equilibrium, and it should continue to remain in a state of equilibrium even after being subject to disturbance. But others may not be able to understand the way it has been defined. we need to get electricity all the time in order to get, so we need to make the grid stable. That's how lay persons can understand this definition. So these two are the things I would like to focus today. The first in EVs, what is the need of AI ML? And this particular slide gives you a general things about EVs. Of course, many of us are familiar with this thing. And if you look at the last point, it requires an efficient battery management system. That's very much required, because the battery is going to is an integral, is a vital component of EVs. So the battery pack, it comes with the pack. So the battery pack needs to be managed properly. For that, we need to have an efficient battery management system. So in order to have a efficient battery management system, the estimation of its state of charge, particularly, and state of health, and those two things are very much important. If we do not estimate them, or determine, you can say, them properly, we may not be able to develop an efficient battery management system. That will lead to other issues, overcharging a battery, and then without knowing the actual thing, we may end up in discharging to the lowest possible value, and that will spoil the battery's health cycle. So in order to take care of battery packs effectively, so we need to have an efficient battery management system. That's critical. So there's no doubt about that. Of course, these are the reasons why we need to move towards EVs. And when they start interacting with the grid, as I said on that day and today also, when they start interacting with the grid, unless we know EV's state of charge, particularly SOC, state of health is required when they are involved in two modes of interactions with the grid, charging and discharging. So health is also important. So charge is required so that you can avoid, because nowadays people are cautious about range anxiety problems in EVs. So those things can be addressed if you can estimate it accurately. That's how this problem has we thought of working on this problem. And this will also help us, do various other things. So now that's why we started working on this particular problem. It will help us identify its optimal battery usage if you know the accurate value of the state of charge, and we can estimate how much range the remaining charge can be used. And the second thing is it helps in preventing overcharging and discharging, so that its life can be extended. And also, if EV users come to know about SOC accurately, users can plan their journeys ahead. And what it does is it indicates what is the level of energy level in the battery. That's how it does. And if you have used any EV, or if you would like to see any EV, you can see the SOC on the dashboard, right? So there we thought of using machine learning model in estimating that particular thing. And similarly, the second component, apart from charge, state of health is also important. So this shows how efficiently we have used it, and what is the remaining health of that battery, so that we can, because the important thing is, as I said, battery pack, and we can think of replacing if its health is not proper, or we can do some maintenance. And once they start aging, its performance will continue to decline. So we have to estimate its health also. And because of that, state of charge estimation and state of health estimation, these two things are important aspects, particularly in battery management system. That is how we started working on this. Now, how to calculate state of charge? There are various methods by which we can do. Conventionally, it has been done using Coulomb counting, that is charge counting method, and by using open circuit voltage measurements, by which we can estimate or calculate its SOC value. But these methods, you can say, they're conventional methods. Of course, they can be done with the help of some measurement devices, sensors, with the help of some sensors. But any measurement, every measurement is subject to some, errors. And they are subject to noises. So they may lead to, they may, they have some lot of advantages and disadvantages. Particularly, these two things have disadvantages in terms of measurement errors and noises, and that's why we need to go move ahead with a new method which can overcome the disadvantages of the existing one. And if you look at the definition of state of charge, it's nothing but its current capacity as well as its capacity at full discharge that is defined by this equation given in equation number 1. And it also varies from a battery to battery. It depends on the type of battery. For lithium-ion battery, this formula has been in use, state of charge in terms of percentage. By using charge values, we can find out. For lead-acid battery, it's based on the battery's current voltage and voltage at full discharge. So by using these formulas, we can calculate the value. And state of health can also be determined by using some conventional techniques with the help of capacity testing and with the help of internal resistance measurements, by which we can determine its state of health also. But the problem with the conventional method, as I said, the state of charge estimation, here also we need to, it involves fully charging and discharging the battery to measure its capacity. So fully charging and discharging, will lead to other issues. And moreover, the implementation is also an issue, particularly when it comes to the conventional techniques. So as far as the formula is concerned, this is the formula to find out state of health, maximum charge to the rated charge. It is expressed as a percentage. So normally state of charge and state of health are expressed in terms of percentage. But when it comes to methods, if you classify the methods of SOC estimation as per the literature, it can be, the methods can be classified under 5 categories. One is based on lookup table methods. By creating a lookup table, we can determine its SOC. The other one is the Coulomb counting method, the ampere or integral method. By integrating the charge over a period, and we can find out its SOC. And the third approach is using state estimation, because we need to estimate, instead of measurements come up with some errors, noises. So those measurements are not perfect. So based on the measurements, we can go for estimation approaches to accurately estimate. Instead of directly measuring, after measuring those values, we can use some estimation techniques, and we can estimate the values close to the actual values. So under this category, they come under the category of filter-based methods. And there are various methods, that have been proposed in literature. And the extended Kalman filter. Kalman filter is a very good filter, filter. So people have proposed many basic Kalman, an extended version, and then various other versions of Kalman filter for resource estimation, particularly in electric vehicles. Apart from that, also they also proposed various researchers have proposed observer-based methods also, by using recent control system methodologies. With the help of that also, they started estimating this was. But even though they have been in use for long, that including conventional as well as filter-based methods, but nowadays more attention has been given towards data-driven, towards data-driven approaches. So why should not we use this way? instead of going into this one. Of course, that's how people have started you applying, particularly AI and ML for this particular problem. For this problem, of course, it has been used across all the things, as I said. But here, more attention has been given, like a black box approach. So under this, many things have been proposed. ANN has been also proposed to estimate SOC and support vector machine, first logic, deep learning, and so many things. Was here I listed only a few. So the data-driven methods are getting much attention nowadays because of its simplicity. Implementation is very simple. You can implement it on time or an online estimation method. Of course, it requires, the problem is, as we all know, we need to develop a model. That the model has to be trained first. So in order to train the model, we need to have a large data sets. So once you can generate a large data set for a particular type of battery, after that, when the model is trained with the large data sets, then the models can be deployed in real time to determine or to estimate SOC. So these things will overcome the drawbacks of this. Maybe a drawback in data-driven methods or machine learning-based approaches. It's developing a robust model and then creating a data set containing various cases. That may be a difficult thing, but once they are available, these approaches shall be better than the conventional one. That's how people have started using and giving more attention towards data-driven methods. In that way, we have also started working on developing a model for estimating SOC of a particular battery. Of course, when you develop a model and when you that model has to be tested, trained and tested for a particular thing. So when you do, so because there are different types of batteries, so those batteries, these batteries have different dynamics. Lithium-ion battery has a different dynamic than the lead-acid battery. So maybe that model, if you want to make it robust for all things, then it has to be tested and trained and tested with various data sets. It may be a difficult task. So, but it's doable, but it is a difficult task. So in this line, we have also started using this. And what we have done is, we have, and then here in this slide, I have given the advantages. Specifically, I have given advantages of this one. And later on, I will talk about the advantages of what I said about data-driven approaches. But the problem is, the method is, the only thing is, system modeling is, we need to have a proper model for battery. If you do not have a proper model, of course, whenever we model a system, we model with some, making some assumptions. So if you do with those assumptions and then develop a model with that assumptions, that model may not be suitable for this particular filter. So that is why this method, particularly this method, fails in that case. And also it requires more computational resources. Though it has some advantages, it has some drawbacks. And then it also performs poorly if dynamics are not well understood. And also, that battery dynamics change with respect to its charging conditions also. At particular charge, its dynamics may be different. That means the model may be different. And then at a different charge level, its model may be different. So it also varies with respect to charging conditions. So the dynamics need to be taken care of. And as I said, computational complexity is high, particularly for this thing. Then when it comes to estimating the state of health, here also, estimation can be classified into two different types. One is direct measurement methods. The second one is indirect analytical methods. In direct measurement method, we can measure its health by using capacity measurement and then internal resistance and impedance. These three methods come under the category of direct measurement methods. In the indirect and analytical methods, there are three categories. One is model-based methods. Of course, model-based method means we can use the models which we have developed for the state of charge estimation by using filter method. After that, then later on, we can use filtering techniques. And data-driven approaches. Some researchers even have combined both model-based as well as data-driven approaches. They have come up with hybrid methods, of course, in order to improve the performance. So SOH estimation, can be classified broadly under these two categories. Now, this can be the current and voltage measurements. We can also combine with some machine learning approaches. But these machine learning techniques have some leverage because if they are trained with some large data sets, they can predict battery degradation patterns efficiently. These methods are better. Of course, these methods, the only thing is they need to be trained with some historical data. Once they train, then we can go ahead with this thing. Now, equivalent circuit models can also be used for SOH estimation. Once you get the proper equivalent circuit of battery, but from which also we can get, and that can also be integrated with some control algorithms to get an improved battery management system. But the only thing is we need to understand the system properly, as well as the parameters need to be estimated accurately. So these things bring some difficulties in adopting this particular method. As the same problem what we face, the dynamic behaviors of the battery model. Of course, getting an accurate model can be complex. It's, of course, whenever you get an accurate model, it may be difficult to solve it, or it will be difficult to implement in real world. Moreover, once the batteries start aging, the models may become outdated. So they also struggle with some non-linearities in the battery technologies. So these are the limitations of equivalent-based circuit models for SOH estimations. That's why machine learning models have become more popular nowadays. So they did not worry about any relationships because they, based on the supervisor or unsupervised learning, the models themselves understand the relationship between inputs and outputs. Once they understand the relationship by studying the data sets, they themselves will come up with various solutions. And then they can adapt to various conditions, depending with respect of batteries' health also. Whether they are aged or young or doesn't matter, they can adapt themselves. The algorithms can adapt themselves. Once they understand the relationships. Till they understand relationship, it may be difficult. So how we can make them understand the relationship? By training with large data sets. And in the advancement of recent communication as well as information technologies, it's not a big thing to have a large data set, and with the help of sophisticated computing technologies nowadays, training a model with a large data set may not be also an issue nowadays. And then when it comes to machine learning techniques, though there are multiple things, here I have given only few because these two things are very popular and they are they have been applied or used in various applications, particularly CNN, convolutional neural network, the long short-term memory model involves. I think they adapt supervised learning. If you have a data set with some labels, they can be adapted and employed in estimating both state of charge and state of health. And we can also use unsupervised learning techniques if the data set doesn't have any labels. And we can also use the techniques those models also, to train and then later on understand the relations between them. And some researchers have also proposed hybrid models in order to improve the accuracy, right? And then overcome the drawbacks of the individual models. The drawbacks will come in testing, in training. So those things can be, in some models may find it difficult to understand the relationship. So in those situations, hybrid models, combining two models may work better. That's why researchers have proposed many hybrid models also to get an enhanced accuracy. So if you look at the advantages, high predictive accuracy. That's the important thing. And the second thing is they can accommodate any kind of relationship between input variables and output variables. It doesn't matter, even they're related with some complex relationships also. Whereas in other approaches, conventional approaches, unless we know the accurate model, exactly capture the dynamics of a particular system or any battery, in this case battery, that model will not be able to work perfectly. But here, these models can accommodate any kinds of relationships with some caveats. That means they should be tested with, trained with some large data sets. And it has a lot of flexibilities. Later on, it can be extended to various other situations also and other operational conditions. That is why, since it offers high accuracy, so we, even researchers have felt, we also felt that, okay, it may be an important thing, particularly in a battery management system. Of course, it has some challenges, though there's a lot of advantages, some challenges these techniques have. Sometimes the data what we get, so we need to generate the data. If you want to really develop a robust model, sometimes you need to generate a data set. Sometimes you generate various multiple data sets. And when you generate that, remain, the generation availability also sometimes they pose some challenges. Sometimes, fitting, the role fitting issues can occur, particularly in data, so that will also create some hurdles in understanding the relations between the variables. And then, as I said, computational requirements to train and test, even though we have sophisticated technology, but sometimes they are difficult, right? So their cost is high. So in order to have that one, we need to have a robust infrastructure, and it's one of the challenges. But mostly people use this as a block box approach. But people may not be able to understand its nature. So stakeholders sometimes they find it difficult to understand its prediction. So that is also one of the challenges. Okay, having seen the advantages and disadvantages, advantages are somewhat better than, or you can say advantages outweigh the disadvantages, considering that recently people have started using it and maybe implemented in some vehicles also, maybe in the future, maybe adopted in real time. So this is how it works, how the topology, if you look at the topology of estimating SOC of an electric vehicle battery pack is, first we need to get some data, we need to acquire some data. Mostly what kind of data we need? We need to measure voltage, current, temperature, and some standard strength charge. These four things are required. So we need to acquire this data. Once the data is acquired, what we need to process the data. So that measurements, of course, they may have some thing, we need to label them, we need to cluster them, some pre-processing is required. Sometimes there may be some outliers in the data sets. Outliers means some data may not be accurate. And then we need to first study and analyze the data. So data processing is very much needed. So you cannot go directly with the data, you need to do some processing for the data. And then once the data is done, it's nothing but creating a proper data set, you can say. Once that is done, what we do with the help of that available data set, we need to train the model. So here I was given many methods, but though suppose you take any particular model, you train it. You train the model with the pre-processed data set. Once that is trained, then of course it will give some estimation value, and that we have to check. There are several metrics to check whether the developed model is working perfectly or not. And there are metrics. Normally, people use mean absolute error, mean square error, root mean square error. So these are the metrics. Of course, there are several metrics, and there are these three metrics are also important metrics. Maybe they are also important. They are important metrics. These are the evaluation criteria. By by finding out these values, then we can say that this particular model is working perfectly. Or if they are not working properly, then we need to improve these metrics by developing a better model. This is how the process goes. First, acquire some data, process it, train it, check, find out those metrics. So now, what we have done is in our work is, once, if you look at the previous topology also, here, normally 80% or 70% of the data set is used for training before it is adapted or employed in real-time applications. So first 70% of the data set is used for training, and the remaining 30% used for testing. So you need to test it also. Once it is trained and tested satisfactorily by checking the criteria, then we can adopt it in real time. So once you have, after that, it will be able to determine, estimate SOC value by if you are providing, if the model is provided with these measurements. If you use a voltage, current, temperature reference, automatically it will estimate and give the values, because it is already understood the relationship between all those things. These are the input quantities, the output quantity, the SOC, and yes, the model itself has understood the relationship, irrespective of linear or non-linear, whatever be the relationship, it has already understood. That is how we train and test it. After that, you can adopt it in real time. That's how it goes. So now what we have done is we have done with, we have used some two models, random forest and then backpropagation neural network. These are all the popular machine learning techniques. We trained these two models with some data sets. So for this work, we have used data sets which are available in the public domain. We have not generated our own data sets. Sometimes generating data sets may be a difficult task because you have to generate under certain conditions. Okay. So some people sometimes use the publicly available data sets. So we have used the data sets available in the public domain. And if you look at the true value and the predicted value using these two methods, random forest and backpropagation neural network, and if you look at the SOC for a different time period, and then based on the condition, you can see moreover, both the methods are most able to predict the true values of SOC. And then if you look at the root mean square error, it is 5.64%, 7.04. Of course, you may think that, okay, it's high. Of course, there is room here to improve minimize this error by developing a better model. We just applied these two methods. This is an application of machine learning technique for this particular problem. And we also use the same model to predict state of health. So if you look at the state of health also and measured and predicted value, if you look at the predicted value and measured value, are almost the same, but they are not accurate, they are not exact, but they are able to predict it. But here also there is room to improve the accuracy by developing a better model. But it doesn't require any complicated modeling. That means it doesn't require any accurate modeling. Its implementation is also very simple. So the only problem is you have to be trained with large data set. That's it. That is the only drawback. So we applied to a specific problem, state of charge and state of health. And here also we have used a particular model, CNN model, to predict the state of health of a battery. And then we calculated its root mean square value to check whether it is working perfectly or not. So we have shown only results of that one, because measured and predicted. though we have done it, we have applied two methods, two models, LSTM and CNN. Here we have shown only for the graph represent only CNN. If you look at the root mean square error value, it's 6.5% and 5.94%. Of course, there is still room to improve the performance by developing a better model. Even many models have come up. There's many new lightweight models, ultra lightweight models, particularly computer science researchers, develop multiple models. So, many are there. These are all you can say maybe 2-3 years old. Now many new models are there. So now, these two findings, what we have found by applying a machine learning model for this particular application, these findings have shown some directions for any researcher, for any prospective researcher or faculty members or students. Of course, there is still room to improve the accuracy by developing better models. We can improve the prediction accuracy also. And because of its, you can say, heavy offline training, but light online implementation. So when you want to implement it online, it doesn't require much thing, but it has to be sufficiently trained offline with a large data set. You can say heavy offline training, light online implementation. That's so that it can be integrated in real-time application. And if you can get better data set by including various chemistries and dynamics of batching, you will be able to develop a better model, or already the developed models can be trained with those sets. So here we need to have some collaboration between academia and industry. So that will help us determine or identify some better management systems, better management systems. This is our future directions, particularly in this topic. When it comes to machine learning applications, there are two important takeaways. If you can develop, you can get a better data sets containing, incorporating accurate modeling of batteries, and then developing a better model. There is still room for develop better methods in terms of SOC and research application. Okay, so quickly we can summarize the traditional methods have some drawbacks, and then machine learning techniques, they're better. That's how we can say. And of course, it has also some drawbacks in terms of computational technology, computational facility, as well as data sets. Now, the second problem is, that is the first one. The second problem is, it's a completely different problem. Of course, that one is related to EVs. The second problem is something related to stability. This curve may be familiar to people who are from power system background, or those who have studied, undergraduate in electrical electronics, electrical engineering. They may have seen this particular graph. So if you are from different background, you may not be able to see it. You may not be able to get it clearly. But for electrical engineers, this curve is somewhat familiar. This curve is called power angle curve. So power angle curve, you can see, I have shown two curves. One is pre-fault characteristics, that is in blue color. The second one is in some more violet color, that is post-fault characteristics. So during fault characteristics, here it is shown on the x-axis now. That means during fault, the power transfer is zero. Sometimes there may be a situation, I will explain. There may be a situation when there is a fault on a bus, or you can say on a node. If there is a fault on a bus or a node, that means let us assume that the fault is of a three-phase ground fault, three-phase short circuit fault. So if there is a three-phase short circuit fault, all the phases are short circuited, and so let's say there is a dead short circuit, then that particular node, if it is connected to ground, then there will be, that node voltage will be zero. So if the node voltage is 0, sometimes it happens. That is the most severe fault. 3-phase short circuit. Then the power transfer is 0, will be 0 because it's directly proportional to the product of voltage magnitudes. If the voltage magnitude is 0, then power transfer is 0. So that situation may also happen. If that situation, that is the worst situation, that is very rare. If it happens, the system, particularly in the power system, in the current system or in future systems also, there will be a lot of synchronous machines. So the system balance will get disturbed. What is the balance? At every condition, you can say, if you talk about from synchronous machines perspective, input and output should be equal. Input is mechanical input, output is electrical output. And that balance has to be maintained constant at every time. If there is any mismatch or imbalance between those two things, that particular machine will either accelerate or decelerate. The rotor, you can say, angle will undergo some oscillation. If the fault is severe and if the fault is a 3-phase short circuit fault, the fault power transfer will be 0. In that situation, the machine will accelerate fast. And we need to make the system stable so that we can continue to supply electricity to consumers without, any problem. So in order for that, the grid has to be stable. So to make it stable, what you have to do is, this is the problem, that particular fault has to be identified. The fault can happen anywhere, maybe on a transmission line, maybe or in the transformer terminals or generator terminals, or maybe any place. So that will affect the entire dynamics of the system, the grid, you can say. So the fault has to be identified and isolated quickly. If it is after identification, it has to be isolated with the help of circuit breakers. So once the fault is clear, the machine initially it was in a stable condition. It has been disturbed now. So that means it must have gone some acceleration, or it must have undergone some acceleration. And even after the fault is clear, because of the inertia associated with the large machine, the rotor dynamics, it will continue to accelerate. And sometimes, even after the fault is clear, sometimes we find it difficult to have a stable grid. It depends on the nature of the fault, type of the fault, and location of the fault. So these three things, and time at which the fault is cleared. So those 4 things are very, very important. So here, first we need to see, we have to clear the fault before a particular time. So that particular time, from a stability perspective, from this perspective, people say, particularly power system engineers say, critical clearing time. So that can be found by using this curve. That is how this has been given. By equating these two areas, that is accelerating area and decelerating area. So once the fault is clear, that means the system network topology will undergo some changes. The power transfer will not be the same value before the fault occurred. The power transfer will be different. So for that situation, we have to check. That is how this violet color graph has come. The pre-fault one is this one. The power transfer before fault is, let us say, in terms of per unit, 2 per unit. After fault, it may be 1, it may be 1.5, or maybe the same value, depending on the clearance of fault and then type of fault. That also can depend on the condition. Sometimes less, sometimes equal. But right, in this case, it has been shown very less value because the line has been taken out of surface. Now, by equating these two areas, we can find out the critical clearing angle and critical clearing time. Why we need to focus on this time? Because this time is very much important to design a protection system. So all the protective devices in any system, power systems or smart grid, suppose smart grid is equipped with some kinds of synchronous machine-based generation. It may not be from thermal power plants. It can be from biomass plants also. But there also we are going to use synchronous machine. So that particular, there is a fault. That protection system should clear the fault before the critical clearing time. So that is why this critical clearing time is very important to have a stable grid. So this has been done identified conventionally. This is for a small system. For a large interconnected system, for a system having multiple generators, we need to find out efficiently. So we thought of applying a machine learning model, machine learning technique to determine the trajectory or to determine whether the system will be stable or not, even after being subjected to disturbance. So that is how the idea of applying machine learning technique to this one has been, has come to our mind. We started working by reading some literature. So, as I said, if the rotor angle, this is the curve with respect to rotor angle and time, delta versus t. This curve is called swing curve. The previous one is called power angle curve. That was between P and delta. This is between delta and T. And if there is a disturbance, before disturbance, the system is at some angle. This system was working perfectly. The angle, rotor angle was constant. Once there is a disturbance, the system can undergo, continuous acceleration. That means the rotor angle can continue to increase exponentially. This will lead to an unstable grid, an unstable system. Right? This is an unstable system. This should be avoided. Of course, it can also happen depending on the nature of the fault. And if sometimes if the fault is clear, the system may come to the same state or an acceptable state, saying the same state or acceptable state after undergoing some decaying oscillations. So now here, what we have done here is we wanted to, predict the rotor angle characteristics over a certain period of time in the future after the rotor, the generators are subjected to, or synchronous machine, or the system is subjected to some faults. So this is very much required to maintain a stable grid for power system engineers. This is very much needed. We need to know whether it undergoes, continually increased value of delta, exponential increase, or it undergoes a sinusoidal decaying sinusoidal response. You need to know this one. So for this, we wanted to use this thing. This will help us understand, particularly from power system operators' perspective, we can understand its stability, whether it undergoes decaying oscillation or increase. And this will also help us implement some preventive control measures. So this is stability study. Once you know that one, by simulating that one, you can do some preventive control actions. Suppose that that particular scenario happens in real time, so we can prevent it. That's how this will help us in doing some preventive control techniques. And also it will help us improve fault response. If you can predict the trajectory. Trajectory means what we are going to do is we are going to predict this trajectory, whether it will go this way or this way, without solving it conventionally. And we are going to use a machine learning technique. Because conventionally, I will explain what is the difficulty in the conventional approach. But these are the things why we need to predict it. Okay. And when it comes to power systems, then there are multiple stability studies, and the rotor angle stability, particularly maintaining synchronism between various machines, particularly synchronous machines. In an AC system, synchronous machines are inevitable. Even in interconnector system also. AC, DC also. In AC systems, synchronous machines are inevitable. So the rotor angle stability is a critical factor. And that determines reliability and other things also. So if you can predict rotor angle deviations accurately without solving it, it will be a good thing. And then we wanted to simulate system and generate some various conditions so that we can apply some machine learning techniques in real time. That's how we thought of working on it. So if you look at the different techniques available in the literature or in the conventional way, you can say, conventionally it has been done by the type of time domain simulation because it's a dynamical study. The entire system has to be simulated. It has to be solved using some using some dynamical equation and dynamical concepts. So it will be a difficult task. Sometimes it's a humongous task. So time domain simulation is currently being used. And then direct methods also, sometimes they use direct methods and equivalent methods. So the big system will be converted to an equivalent based approach, like how we use Thevenin equivalent approaches. The big system, any big system can be converted to a simple system, provided the system is linear, bilateral, containing linear elements, bilateral, elements we can simply replace the entire system with a simple system, and then we can use it. Similarly, equivalent methods have also been used recently. But the problem with first three, I will list later. Recently, data-driven approaches, like the way data-driven approaches have got much attention in SOC, SOH applications. This is one of the applications. There are multiple applications. So here also, data-driven methods have got much attention, particularly in this problem also. So there are four approaches by which we can predict the trajectory. But first, time domain simulation, it actually simulates and gives the value. It doesn't predict, it calculates the value. It's a difficult task. Okay. Other two methods, direct method, equal method, they use some approximations to find out that one without solving those dynamical equations directly. We wanted to test this one on a standard test system. When you develop a model, first, after developing the model, you need to study this one in a standard test system. So we use this particular test system. Power system engineers may be aware of this test systems. So it's one of the standard test systems, particularly stability studies use this one. So 39 bus New England system. So you can see this system is a very good system. We can study the stability particularly. If there is any problem in particular, it has been divided into 3 areas. They have been shown in, including this one particular one generator, also 4 areas. They have been shown in different colors. And then here there are 10 generators associated with this particular system. So this system is used for this application. And it's a complex system. That's why particularly stability researchers use this one. Moreover, if you can test your model and then for this particular system, and then you can see that it's better. So what we have done is we have proposed a hybrid model. So why we wanted to propose hybrid model is because here we need to get the accurate values. So we applied some individual models like LSTM, CNN models for this problem, and then we found some we didn't get the accurate results. That accuracy was not so good. So we thought of combining it. Of course, if you combine, it takes some more computational time. That's true, but of course that is only done in offline. So we need to worry about whether it will take more time in real time, because once it is trained offline, then we can implement it in real time. So it doesn't take much time. It gives a value quickly. So that's why we combine. So what we did is we combined LSTM and CNN model. That's how we proposed hybrid model. And if you look at the architecture, so it takes some inputs. It's a general architecture of this model. It's the layer. Here also number of layers, number of neurons, and those things can also be found out using some techniques. So we have used an optimization technique to find out the number of layers, in these 2 blocks, and then we use this one and to find out the relationship between the input and output. So the parameters I've used is, and the input data is 10 because of 10 generators. We took the rotor angle from all generators, because when there is a fault, all generators angle will undergo some oscillation, right? So if you do not take some suppose if you do not take some steps, so they will disintegrate, and then the entire network will be disintegrated, and it will lead to an unstable system. This system will collapse. And then if you look at the number of units, these units can also be determined with the help of some optimization techniques, how many units will fit for our own things. So we have used some parameters, we identified some parameters, we have taken some parameters from the literature. And then we tested with a loss function to check whether there is any loss in the training and validation. So we trained with multiple things, and then we validated with all those things so that it can be applied in real time. So if you talk about the drawbacks of this, I didn't tell you. I will tell you only in one line. Particularly in time domain simulation, direct methods, equal methods, they are in use in real time nowadays. They're computationally complex. In order to solve the system, they are computationally complex. Even with sophisticated computing facilities, they're still computationally complex. They're difficult. The computational burden alone forces researchers to think of simple methods. That's how the data-driven methods have got much attention, particularly for this problem. So here, the only thing is you have to train with large data sets offline. Once it is done, then you can directly apply in real time without much difficulty. You can easily find out, predict the row triangle trajectory quickly. So we tested, we found that there is a significant reduction in loss after that multiple trials. So we compared the training loss and the validation loss. And then you look at the angle. I've shown it for only 8 generators. Angle 1, angle 2, angle 3, angle 4, angle 5, angle 6. These are all different generators, row triangles. And then we ran our model on this system to predict. We created some faults on that system. We created a severe fault at different buses. Before that, here, the data set what we used to train our model was not publicly available. We ourselves have generated the data set. We have generated data set by using a Simulink model, by simulating that 39-bus system on a Simulink platform. We generated various by data sets for various conditions by simulating faults at various locations, at various places. It took a lot of time, and we generated data sets. And with the help of the data sets, we trained the developed model. We trained it, and then we tested with 30% of the generated data sets. We found out, that's what I showed you in the previous slide, there is a loss and a training loss and validation loss. We went ahead. So we applied real time, and then we found that you can see the angles. And there are 2 approaches. So we also did both approaches. One is we can predict whether the system will be stable or not. That is a binary problem. Suppose it is subject to disturbance, we can predict whether it will be stable or not. Or if you want to determine the trajectory, that means trajectory means you should be able to predict the value of delta angle for a different time period, for different time instance in the future. So that also we can do. So it's 2 things can be done by using these approaches. We can use it to say whether it is stable or not, or we can say that we can predict the row triangle trajectory also. So both the things can be done with the help of the models. So both the things will be helpful to the power system operators, that will help them take some decisions. So these are the things we verified with our things. So we can summarize the results, our results findings. These are our results findings. So we did these things on standard systems. That's why we could summarize based on our results findings. Of course, these things will under publications and the consideration of publications. This is very important for maintaining stability, particularly in an AC system, interconnected AC system. Low voltage stability, frequency stability. So they are also important. Row triangle stability is also very much important, particularly in maintaining synchronism. Conventional methods, as I said, particularly time domain simulation, very difficult, computation intensive to find out the row triangle trajectory. Even if you use a sophisticated system, it will take more than sometimes hours to find out the value. So this problem, you have to, if you want to make the grid stable, then you need to identify the value quickly. But when you use the machine learning approach in the machine learning models, if the models have been trained with some large data sets, you can adopt them in real time. You can get the values quickly. That is how they are better, much better than the conventional methods. And they will help us. They will help particularly operators with some signals, so that they can take some remedial measures, or if they can simulate it, they can do some preventive measures to make system stable and then resilient. As far as this work is concerned, we have used with some standard models. Even researchers, if suppose there are some researchers in this particular topic, there is a room, still there is room to develop a better model, and then test it as standard large data sets and apply it on standard test systems. Right. So as far as the discussion and conclusion are concerned, in this talk, I've used, particularly with the help of my PhD students and BTech students, we have developed some models for specific applications. Because when it comes to specific applications, the machine learning models, we cannot directly use the models available in the literature or in the what is available in the public domain, because they are dependent. You have to tune those models to fit into your particular problem. So as far as these two problems are concerned, SOC and SOH estimation, and then rotor angle prediction. So we need to tune those models and test it, and then check. And they've given some but significant results for that one. And these are the references, and some of the references you can see. And then our findings have been published in conferences, and they will also publish in some journal publication. They're under publication stage based on our work. These are the references for the today's talk. I think today I could complete in 1 hour. So if you have any questions, you can ask based on the today's presentation.
Good evening, sir.
Please.
What are the database required to use machine learning for analyzing the power system stability, sir?
Particularly here, you need to have, we need to understand the relationship between rotor angle. That is the main thing. So you need to get the relationship between rotor angle, how they behave. So mainly you need to capture the rotor angle. For that, you cannot directly get from this thing. So you have to get from PMU, phase and measurement units. So in our system, we absorb from this one, but in real time, so you need to get voltage and current angles. From that, you should be able to detect the rotor angle. So you need to do some measurement there to find out the delta. Mainly delta, we need to predict it for power system stability studies.
Participants?
Sir, can we have database of rotor angles from the previously occurred events of faults in the power system?
Of course, when you want to apply this machine learning model, first you have to test and train. So you need to create a data set by simulating at different conditions. For various scenarios, you have to simulate. And then when you apply it in real time, so whatever be the fault, whether it's 3-phase fault or single phase to ground fault, line to line fault, any fault. So it will be that particular model should be able to determine the trajectory of rotor angle over a period of time. Suppose you want to find out the trajectory for 5 minutes in the future. So that can be found using this model, provided if it has been tested with some data sets.
Okay, thank you, sir.
Okay.
Participants, anybody having question?
Research, can you suggest some research topic in electric vehicles? There's a question from one of the participants. So SOC, HOS estimation, by using machine learning, I'm talking about, we can use, but I'm also working on electric vehicle scheduling, EV scheduling. There also we can use machine learning, EV scheduling, because when it comes to integration, there will be a lot of issues. So as I said in the first talk, some kind of coordination is required. That coordination can be a very good research topic, like EV scheduling. And when it comes to battery management, particularly in the power system side, developing an efficient battery management system, it's a very good research topic. If you talk about from power electronics perspective, developing a wireless charger, fast charger, right? And developing a battery management system is also it's an integral component of both power system and power electronics. And developing a controller, these things are very good research topics. Or developing a dual active bridge converter for EVs, because EVs batteries need to be you need to interact with the grid on both sides, charging and discharging. So development of a dual active bridge converter, efficient converter, that is also a good research topic, particularly EVs. And then if you talk about motors, development of an axial flex hub motor also is a good topic for EV, because nowadays you need to compact all the motors inside the wheel so that its weight can be minimized, particularly in that machines and power electronics perspective. In power system perspective, development of fund management technique, integration issues, and particularly EV scheduling, those things, SOH estimations, those things can be a potential research topics. If anybody else has any questions, you can post it in chat box. I'll be very happy to answer. If there are no questions, we can wind this session up.
Okay, sir. Thank you, sir. Thank you for your presentation, sir.
Thank you all for patiently listening to my talk. Thank you.